All right, so I have shared my VS Code window. So this is my code base. So I have a source file called c2g.cu, which implements both color to grayscale kernel, as you can see here, and the blur kernel, as you can see here. But before that, let's review the CMake file. So here, some standard lines, the version of CMake, the version of C++, the languages, things like that. And first, I need to use this find package to find the CUDA toolkit, but you have to make sure that CUDA is installed on your system because I'm going to work with images. So I also work with this find package OpenCV. So make sure that you have OpenCV also installed on your machine. Then I add executable for this C2G .cu file, and I just name it C2G. And finally, you have to link CUDA runtime library and the OpenCV library to this C2G executable. All right, and by the way, this is my image that I'm going to work with it. So let's see how we can write this color to grayscale and also blur kernels. Okay, so these are the header files first that I need to include. So these two are standard, but I need to include these header files for working with OpenCV. And then I include this CUDA runtime to work with CUDA and CUDA internal variables. All right. So the first kernel is this color to grayscale kernel. So in this case, we have an input image, right? And an output image, both in pointer of characters, right? Unsigned characters. And the image width and the image height. So these are my inputs to my kernel. Then I need to find the column index and the row index of like my threads within this block. Then I check my boundary conditions. And here I do a slightly different than what I showed in the slides. So here the input image is a colored image, and which is like its size is width times height times 3 because it has two channels, R, G, and B. So because of that, I need to find the index of the pixel, but also considering the channel, the channel RGB. So that's why I multiplied by 3. So this is the index of the output of the input image that I want to work with, right? So then I find the R value using the input in this IDX. Then input of IDX plus 1 would be the green channel, and finally I have the blue channel, right? So now I have the value of R, G, and B. Then I just need to convert the color image in the colored pixel into the grayscale pixel. So I can do it using this equation from image processing. And then this gonna be my output pixel, right? So here, because the output image is a grayscale image, so you don't have these channels. So that's why I just use this y times width plus x, right? Row times the number of columns add with this column index. All right. So this is the implementation of the grayscale one. And now I'm showing you the implementation of the blur kernel. So again, I need to check, I need to obtain the index of the column and the row index of the thread within this block. Then I check the boundary condition here, right? Then I need to identify the index of the pixel in the input image, which is a colored image. So I define a variable for the count, so the number of pixels that I'm computing. Uh, and then I have three variables for summing over R, the red channel, the green channel, and the blue channel, right? So it's slightly different than what you saw in the slides. Okay. Then this 5 is my blur size. So I start from 5 pixels before my actual pixel and then continue to 5 pixel after my actual pixel in both rows and columns direction. Then for each for each iteration in this nested loop, I need to find the actual index of the surrounding pixel, right? So X and Y are the center, which is the actual pixel that like the center of this the square that we are working with, and this using this dx and dy, we check the surrounding pixels. All right. Okay. Then we have the other boundary condition to make sure that our squares are within the image, right? Then because the output image also is a colored image, so we also need to identify its pixel by considering the channels, right? And then we sum over the the R channel, the G channel, and the B channel, RGB, right? And then we count the number of pixels that we average, that we sum. So after that, we need to compute the output image, right? The pixels of the output image. So we take the average over the R channel and then put it into the output matrix. Then we compute the average for the green channel and the blue channel, and then we write it into the output image, right? So a slightly different implementation, but I think it's more readable compared to what I showed you before. All right. Okay, so now let's see the main function, how we can load the image and how we can like get this image values and so on. So the first thing that I do is to find the image using OpenCV. So this is my image file, image.png. So I just need to specify address to OpenCV. Then I can use this imread function in OpenCV and specify that this is the colored image, right? To read the image from my disk into the memory, and OpenCV basically stores this image into a data structure called mat, which is a matrix. And then I check if the image is empty. So if it was empty, then I send an error. Then I just like print two lines. So the first one is like image loaded successfully, and here in the second line, I just print to the screen the number of rows and the number of columns. So basically the image size. Then I introduce two variables, width and height. Width is the number of columns, height is the number of rows. And then I have to specify the image size for the colored one, which is width times height times 3 and times the number of like the size of the character, right? Because I need to have the size in bytes. And then I do the same thing for the grayscale image. So in that case, we don't have this 3 because we don't have 3 channels. So it's going to be 1. And then I have to allocate some memory on my GPU. So I introduce two pointers for the input image and for the output image, right? And then I use this CUDA malloc for allocating memories on the device. So first I just allocated some memory for the input image, for the colored image, and then for the grayscale image, right? So after allocating memory on CUDA, we just need to copy the data from the main memory or the host memory to the device memory. So here I pass in the device address, the device memory address, and then here is the data of my image, which is an array, and the size of the data and the type of transfer, which is CUDA memcpy host to device in this case. All right. So now I'm ready to launch my first kernel. So I define the block size to be 16 by 16 threads. And then I define my grid size using this dim3 type in CUDA runtime. And then I launch my kernel. The first kernel is color to grayscale kernel that I launch, right? Then I use this CUDA device synchronization to make sure that my code synchronizes here and nothing happens on my host unless the GPU part is finished, right? And then I need to allocate some memory using OpenCV for storing the output image on my host memory, right? Then after this kernel is done, I have now the output to be filled with data. So I just need to send the result to to the host memory using this CUDA memcpy device to host, right? And then I just store the image in a PNG file. So this is my matrix that stores the image, and here using OpenCV, I am writing the image into my disk in the PNG format. So this is about the first image, the first kernel. And now I can also call the blurring kernel. So what I need to do is to allocate some output memory for the blurred image, right? Because in the grayscale case, I had a two-dimensional array, but in this case, I also need to consider that the image is colored. So again, I have to allocate some memory on the device. So I use the size of the colored image that I defined here for the colored image. So this number is not different. Okay, where was I? Okay. Then I can launch the blur kernel using the same number of blocks and the same number of threads per blocks. And then I use this CUDA device synchronize again. Then I allocate some memory using OpenCV for the output image for the blurred one here. And then I write the output, the results to the memory in OpenCV that I allocated using this CUDA memcpy device to host. Then I write the output image uh, on my disk, and finally I just need to free up the memory that I allocated on my device. And by the way, the memories that are allocated by OpenCV are going to be deallocated automatically by the library. So you don't need to do anything about those. Okay, so now let's compile the code. Sorry. Okay. So I just need to create a build folder, and then I navigate into my build folder. Then I compile using CMake. So first I need to configure CMake to find my compilers. And then I can use make to compile the actual code. So let's wait until it's compiled. Then I should have an executable called C2G here, as you can see it here. All right, so let's now run it. I navigate out of the build folder and then right? C to G. Okay. Outside. So this should be built and then C to G. Okay. So after executing this program, now we have two images in this folder. The first one is blurred image, and the second one is the gray image, right? So this is my original image. So it's the colored image, right? So if I open this grayscale one, so you have the grayscale version of that image, which I did using CUDA on my GPU, and this is the blurred version of the colored image, right? So you can compare it easily. So this is the original image, and this is the blurred image. And everything here was done in parallel using CUDA on my GPU. All right. So this is actually what I wanted to show you about CUDA programming and working with one-dimensional and two-dimensional data. So this is the entire material that we are going to talk about GPU programming in this class. So in period 2, we are going to have a dedicated course on GPU programming, and we talk about most of the GPU programming aspects in more details. And if you want, you are welcome to take that course on period 2. All right. So this is what I wanted to cover also for today. And thank you for watching this video and have a good day.